In this video, we'll talk about circuits and cycles. We'll look at an example of a circuit and a cycle. And finally, we'll look at an example of the girth and the circumference of a graph, which are related to the concepts of cycles. So just to refresh your memory, hopefully you've already looked at the section and picked up on these definitions. But we have the idea of a closed walk, so a walk that begins and ends at the same vertex. And just like with walks, trails, and paths, we had this sort of hierarchy, right? Every path was a trail, and every trail was a walk, but the opposite was not true. Same thing here is true. So a closed walk just begins, it's a walk that begins and ends at the same vertex. That's the most general we can get. That's the biggest class. A little bit more special is a circuit, which is a closed walk where we don't repeat any edges. That's a circuit. And then even more special than that is a cycle, which is a closed walk in which no vertex is repeated. So let's take a look at this. So let's maybe look at, how about the following circuit, something like U, W. So let's write it down. So U, W, X, Y, W, V, U would be an example of both a closed walk and, let's check this, so U to W, W to X, X to Y, Y to W, notice I've repeated the vertex W now, W to V, and V back to U. So it's a closed walk, right? Begins and ends at the same vertex, and notice I haven't repeated any edges. So this is a circuit of length, and again, the length is the number of edges that are encountered. So 1, 2, 3, 4, 5, 6. Circuit of length 6. On the other hand, we have a cycle, which is a little bit more special. So this would not be a cycle because we repeated the vertex W. So not a cycle. But let's say do the cycle U, W, WX, XY, YV, VU. So U, W, X, Y, V, U. So again, it's a closed walk, and we don't repeat any vertices. Since we don't repeat any vertices, we don't repeat any edges. So this is also a circuit, but it's a special kind of circuit. It's a cycle because we don't repeat any vertices. So this is a cycle of length 1, 2, 3, 4, 5 of length 5. In fact, this is a special kind of cycle. It's what's called a Hamiltonian cycle because we encounter every vertex of the graph. So you don't have to encounter every vertex of the graph. Something like U, W, V, U is a cycle of length 3, which is, of course, a triangle. So, right, we don't repeat, none of the interior vertices are repeated. Of course, we repeat the first and last vertex, but none of the other vertices are repeated in a cycle. So that's, yeah, circles and cycles. So you should see an analog between trails and paths. Okay, so two other properties of a graph that go along with this are the girth and the circumference of a graph. So the girth is, among all the cycles in a graph, find one with smallest length. That length is the girth of the graph. The circumference is the maximum of all the lengths of the cycles. And so for any graph, we can compute the girth and the circumference. So maybe we look at this one as an example as well. What's the girth and the circumference of this one? So the very smallest, in general, the girth is always at least 3. You need at least 3 vertices, or rather at least 3 edges to make a cycle. 1, 2, 3. And so the girth of this graph, if this is G, then the girth of G here, the length of the smallest cycle, is 3. And for any graph, that's the smallest you could possibly have. Other graphs, the girth is bigger, as we'll see in a second. And the circumference is the length of the longest cycle. So we actually found what a Hamiltonian cycle, since we encountered every single vertex of the graph, we certainly can't do any better than this. And so this is actually the maximum length as well. The circumference of G is 5. 1, 2, 3, 4, 5. So that's the longest cycle you could possibly have in this graph. So girth and circumference. So what about, let's take a look at girth and circumference for the complete bipartite graphs. So let's just take a look at, I don't know, how about K2, 3, for instance. And we'll assume S is less than or equal to T for this notation. So K2, 3, remember this looks like this. This is my complete bipartite graph. Bipartite sets of size 2 and 3. So what's the smallest possible cycle I can make? So the smallest closed walk in which no vertex is repeated. So I can go 1, 2. Notice I can't do 3 because after I do 2 edges, I'll be back in the same partite set and those 2 vertices won't be adjacent to each other. So then I'd have to go to this partite set 3 and 4. I should also say here for S and T, let's say 2 less than or equal to S, so at least 2. So this is the best you can do, and in general, this is true for KST, that the best you can do is a cycle of length 4. The best you can do, is, by that I mean the smallest possible cycle is length 4. So that is the girth of KST is equal to 4. So long as S is greater than or equal to 2. What about the circumference? So let's again look at, let's say, K2, 3 as an example. So what's the longest possible cycle I can have? So if you think about this for a bit, you should find that you should start at in the smallest partite set, so in the S vertices, so the 2 here. And what you can do is you can go out to the next partite set, you can come back, since S is at least 2. You can go out again, and then if we had more vertices here in S, you could keep going, but here we don't. And so the best we can do is actually 4. The longest possible cycle we could have is length 4. I didn't have another vertex here. Otherwise, I could have came out and then back to the vertex. So actually, so while we have the girth, oops, I don't use white. Oops, no, not a ruler. The girth of K2, 3 is 4. So is the circumference. That the longest cycle is also 4 for K2, 3. So why don't we look at another one? Why don't we look at K3, 3? 3, do. So what's the best I can do? I go out, I come back, I go out. I don't want to come back, all right? I have another option here. Go over here, back, and then back to my original vertex. So it looked like here, the girth again is 4. Girth of K3, 3 is equal to 4. And in general, again, that's KST, that's the smallest possible cycle is 4. The circumference, though, of K3, 3, in this case, was 6. So we'd like to uncover what this is in general. So for KST, S less than or equal to T, and both at least 2, I'll have S vertices there, and T vertices here. Maybe I have more T than S. But the idea is, and all the edges in between these are here. So I come out, I go back in, go to the other partite set, and I can keep doing this. I can keep doing this until I run out of vertices of S, right? So maybe I've used up this one, and now I come back here, And now maybe I've run out of vertices of S. Maybe I even have some other vertices here, but I've used up all my vertices of S. And so now I'm forced to close up my cycle to get the longest one. So for every vertex of S, I have one edge going out and another edge coming back in. 1, 2, 3, 4, 5, 6. And so what I get is twice the number of vertices in the smallest parsite set. So that is 2s. So while the girth, we just showed the girth of KST was 4, the circumference of KST is twice the number of vertices in the smallest parsite set. So that's 2s. Okay, so that's circuits, cycles, girth, and circumference.